I did something that I called, I worked on something I called developing. So I developed the Direction Predictor Equation, the DPE, Direction Predictor Equation, for a pretty simple example, right? For the A to B reaction where A and B are both gases. Okay, and whenever I say develop the DPE, what that means is you should start with this equation. dG is the sum over I of mu I dNi. So you're basically using the total differential of the Gibbs function, except constant temperature and pressure. That's why we don't have a dT and dP term here. So in this simple reaction, in this simple case, this is the chemical potential of A times the change in moles of A plus mu B dNB. And that's where we started last time. And then, I say this for review for the people who are here, who weren't here last time, but the same people aren't here again. So here we go. I'm going to review it for the people who've seen it already. That we write these changes in moles in terms of the extent of reaction parameter. So this is the change in the extent of reaction, which is a parameter that basically goes from 0 to 1, from the beginning of the reaction to the end. And we set this up, remember, that the total pressure was 1 bar, and at the beginning, PA is 1 bar. And if this were to go to completion, which, well, whatever, PB at the end would be 1 bar. All right. So in a way, you could think about dx is really like dPB in this example, because P goes from 0 to 1 as well, just like X goes from 0 to 1. So, so D, the change in moles of B equals dx, which is the negative of the change in moles of A. So you can always express the change in moles of all the reactants and the products in terms of this extent of reaction parameter by just putting a negative sign in front if it's a reactant, and also dividing by the stoichiometric coefficient, which in this case, they're all 1, so we don't have to bother with that. So, so the next step you do in this would be to write this as dG minus dx, right, plus mu B times dx. And then we get the beautiful expression for the slope of the Gibbs free energy as a function of extent of reaction, right? This is the slope of the Gibbs free energy as a function of extent of reaction. And it is equal, so the dx's are on the other side, and this becomes mu B minus mu A. And then what we do is we use this relationship. This is true for gases, that the chemical potential of component B of a mixture is the standard molar chemical potential of pure B plus something that's like a term that, well, this is the partial pressure of B in this case. It's not the same quite as for a pure substance, but you just have to add this RT log term. And then the same thing for mu A. And what we did last time was we subtracted these to get an expression for mu B minus mu A, which we realize is this very important slope of the G versus extent of reaction. And this turns out to be, well, if you subtract these two, you get the mu B 0 minus mu A 0 plus RT log PB over PA. And this thing here This is just the difference in the molar Gibbs free energy of B and A, products minus reactants. So this is the change in the Gibbs free energy of the reaction, which a lot of times I don't write the Rx in. It's the same as delta G0 for the reaction we happen to be talking about. And this thing, this is called the reaction quotient, because these are all pressures. We call it QP. But if we had reactions with aqueous stuff, we would just call it Q. And so we end up with this dG dx equals delta G0 plus RT times the log of PB over PA, which is RT log of Q. And then I showed you what this portion of it anyway, I showed you, well, I showed you more than that, but this portion, if you look at it graphically, so if you just look at a graph of RT times the log of PB over PA as a function of PB, which is really the same as X. And of course, PA is 1 minus PB, the way we have this set up. So we're really looking at RT times the log of PB minus RT times the log of 1 minus PB, because that's RT log of PB minus RT log of PA, which is the same as this. Okay. So we looked at this function, and it's a really cool looking function. It's negative infinity. It comes to the 0. It goes, it's this very, it doesn't actually intersect this. It just asymptotic to it. Okay, so that's what it looks like. And if you look at this formula up here, this equation, you see that if the delta G0 for the reaction happens to equal 0, then this slope of the G versus X will actually equal RT log PB over PA, which is this thing that is plotted over here. So what I did first was to consider the special case where the reactants and the products have the same Gibbs free energy. So in other words, mu B0 equals mu A0. Okay, and then delta G0 reaction is equal to 0. And in that case, this graph tells you really most of what you need to know. Here is where the y-axis crosses the 0. These values are positive. Okay, these values are negative. And here is where this RT log PB over PA, which would be the slope, right? This would be dG dx if the delta G0 is 0. And so if you look at that, you could see that the graph of G versus X, okay, well, you have the same Gibbs free energy of the reactants and the products. So these two would be on the same level. There wouldn't be any difference, any delta G0 for the reaction. So I might label this as mu 0A and mu 0B, okay? And now I know that at small values of X, like right here, I'm going to have an extremely negative slope. So I'm going to have a very negative slope. And that as this X increases, that slope gets less and less. And the graph, now I'm going to actually draw the graph like a regular person, not just drawing it a little at a time. And it looks something like this, with the minimum exactly supposed to be anyway in the middle. No. Okay, so right in the middle here. Hi, Benjamin. So right now we're about where we were at the end of last class. So anyway, so if there is no delta G zero, if delta G zero equals 0, then dg dx, I'm sorry, then the minimum of G versus X is right in the center. In other words, half A, half B, okay? So here's an interesting question. And honestly, I'm sorry that we don't have enough time to really delve into this further. But you have to ask, you might ask yourself a question, why is there a minimum at all? If this is true, if the Gibbs free energy of the reactants and the products are the same molar, okay, then why a minimum? Why doesn't the G function, get some more room here.
Isn't it because it just matters on the initial and final state?
No, that if all that mattered was the initial and final state, I would say, then maybe it would be straight, Why does it have to have this bend? And we know it does, because if you start out here, it's going to end up here. And if you start out here, it's going to end up here. But the reason there's actual very, very physical reason for that. And the reason is that when G is a minimum, entropy is a maximum. And it's actually the entropy of mixing. There's something called the entropy of mixing. Now, if you combine two gases, say you have gas A and gas B, and let's say that these do not react. So maybe it's like having argon and neon or something like that, where there is no reaction between the two of them. That's not a good comparison. No, that's not good. Wait. No, it's good. So if you started out with something like this, where you have the same pressure and you have a bunch of, neons on one side and a bunch of argons on the other side, and you pull this out, if you calculate the entropy of this whole thing before you pull it out and the entropy after you pull it out, it is a greater entropy after you pull it out. And that's because it's actually a greater entropy to have a half and half mixture than to have 50 on, say if you had 50 of each, having 50 on one side and 50 on the other side has a lower entropy than a mixture, a 50-50 mixture. So it's actually 50-50 mixture has the greatest disorder. And so the minimum is due to that. Minimum is due to the greater entropy for two substances fully mixed than separated. And I know that's a little bit out there and I haven't proved it to you or anything, but it's actually not that hard to show. But anyway, so that's why you don't have a completely straight, you got to think of what is in the Gibbs free energy, right? You have the enthalpy and you have the entropy. Well, if you mix two ideal gases, there's really no change in enthalpy on mixing because there's no interaction. So the delta G of mixing is due to the entropy change on mixing, and all that's because you mix it up and it becomes more disordered. And so the greater the amount of mixing, the greater the entropy. So that's just, this is kind of a little aside that really has not much to do with what we're really talking about. This is kind of an aside. Okay, so anyway, I did go on and I talked about what happens if you have a positive delta G0. So if delta G0 is positive, okay, then you still have this crazy graph, right? It goes through the middle. And this is RT log PB over PA, or RT log PB minus RT log 1 minus PB. That's how I showed it to you, but it's the same thing. Okay. But now what happens is if the delta G, if the dG dx is delta, it's always delta G0 plus RT times the log of, for this simple case, PB over PA. Now, if this is positive instead of 0, then it's like adding a positive amount onto this graph. So you end up with a curve that looks something like this. And you could see that where that curve intersects the 0, in other words, where this, now this is going to be the slope dg dx with that added term, okay? So we're still looking at the slope, but now we have this plus the delta G0 added on. And now instead of this curve going through and hitting the 0, this is the 0 here, at the midpoint, you could see that the dg dx curve intersects the x-axis, right, when it equals 0 at a much smaller value of x. Okay, so that means, what does that mean? So you can draw the Gibbs function. So this is the slope here. This is dg dx. What does g versus x look like? And again, for very small values, you know, over here, when you start this curve, you have a very negative slope, right? These values are all negative for the slope. These values are all positive. So that means the slope here will be negative. Okay. And that slope goes through 0 pretty soon. So delta G0 positive, that means that this difference here, that this delta G0 reaction is positive, goes up for the products. And so you have a situation like this, where now your equilibrium, which is down here somewhere, I didn't do a very good job illustrating that, but the equilibrium is on the reactance side. Okay, and I did this part last time, and this again is like mu0 of the reactance, which in this case is just mu0A and mu0B. Usually it's the sum of those mu's multiplied by stoichiometric coefficients, but we haven't got to that yet. So the equilibrium here is on the reactant side, which makes sense because the reactants have a lower Gibbs free energy. But what does that tell you about the direction of the reaction at any point? So the slope tells you the direction, because what always has to happen is G has to decrease. So here, the slope is negative, all right? And that means that to decrease G, the reaction goes in reverse. See, for G to go down, it has to go backwards because the slope is negative. Here, the slope is, did I say that wrong? The slope is positive here, so it goes backwards. Yes, so here the slope is negative and the reaction goes forward. But for more of the concentrations, right, for a lot of it, the sign is positive. and the reaction is going to go backwards. Well, that's because the delta G0 is positive, but it doesn't mean that there isn't some portion of this curve where the reaction is actually going to go forward, even though the delta G0 is positive. So that's why this is called the direction predictor equation, because knowing what this ratio is, you can tell what the sign of the dg dx is, and that will tell you which way the reaction is going to go. So let me just go through the last part. So this is, again, this is our same. This is the RT log PB minus RT log 1 minus PB, which is the RT log PB over PA portion of the direction prediction equation. And now this is what if delta G0 is negative. And so that means that onto that, you'd have to add on or subtract actually a constant delta G0. And now your curve hits the 0 at a larger value of X. So this means that the equilibrium is really favoring the products more. So here now we have our delta G0, which is negative. So the minimum ends up being on the product side. Well, I didn't draw it too accurately because this is really much more something like that. I don't know. Anyway. So which way will the reaction go if X is 0.2? Well, we're over here. So you could see that the slope is pointing to the right. So here we have at 0.2, this is in the negative region. So the slope is negative at 0.2. So that means if the slope is negative, then to increase G, we have to increase X. So X increases, which means that the reaction goes forward. At 0.5, well, we're over here at 0.5. We still have that same slope. Slope is still negative. So the reaction goes forward. When you get to 0.89, which I'm going to assume this is, because that's what this is over here. Of course, the drawing isn't perfect. Oh, actually, at 0.89, oh, that's equilibrium. So it doesn't go either way. And then at 0.95, now your slope is negative. Okay, so.
You mean positive?
Sorry?
You mean the slope is positive?
Oh my God.
So why would it be
positive, right? At least I didn't say these wrong. Yeah, these are all negative. Okay, yes, it's positive, exactly. So to decrease G, must decrease X. So the reaction goes in reverse. All right, yeah, thank you. Okay. So, and you could see because the delta G0 is negative, it sort of pulls this curve down so that the equilibrium ends up on the product side. So there are many more values of the extent of reaction parameter where the reaction is going forward. I mean, delta G is positive. But there are still portions of the curve where the reaction is going negative. Like when you have all products or mostly products. So the sign of the delta G0 has a large influence on what the direction of the reaction will be, but it is not the only factor. The other term is important as well. And so it's a little more complicated than the Gen Chem idea that, oh, if delta G0 is negative, the reaction goes forward. Yeah, under standard conditions, but not under all conditions. So So let me just mention what happens under standard conditions, because I just brought that up and I might as well. So what happens under standard conditions? So first of all, we have this dg dx is delta G0 plus RT log for this simple case, PB over PA. And under standard conditions, all the pressures are equal to 1 bar. So that means I put in a 1 for here and a 1 for here. Okay, and so this ends up being 0. So under standard conditions, the slope of the Gibbs function depends only on the delta G0. Okay, so that's why we say, you know, if delta G0 is positive, the reaction goes in reverse. And then I quickly have to put in the fine print, which is under standard conditions, because the conditions matter, right? Because not every single condition here is going to have the reaction going forward. There are some where it goes in reverse. Oh, well, this is for the negative delta G0. Let me write that too. So if delta G0 is negative, the reaction goes forward under standard conditions. Okay, and then this is a better illustration of what we just did, right? Where delta G0 here is negative, and for many, many values of X, this is going to the right, but over here it's going to the left, okay? Because you have lots of products. So using this direction predictor equation, we can actually figure out which direction the reaction is going to go at any point, but I'm not really ready to do that yet because I first want to extend it to a more general case. But first I want to say, okay, if we're at equilibrium, okay, so if we've reached equilibrium, we know that this slope here, dg dx, is equal to 0 at equilibrium. And that this is delta G0 minus RT log of that Q, right? That's the ratio at any point in the reaction, okay? So if this is equal to 0, well, when is it equal to 0? Is at equilibrium. So I can change my Q to a K representing the equilibrium constant, and I end up with 0 is equal to delta G0 minus RT log of K, which is Kp in this case, because we happen to be dealing with gases. And so delta G0 is minus RT times a log of K. And this is an equation that you know, you've known about since general chemistry. This is where it comes from. And that's all fine, but that's for the A to B reaction where they're both gases. So what I'd like to do is extend this to more complicated reactions with stoichiometric coefficients that are not all 1. And then I would like to be able to include solids and liquids and even solutions. And we're going to do that all today, okay? So when I ask you, again, I said this at the beginning, but when I ask you to develop the direction prediction equation, I always want you to start at the same place. dg is the sum over I mu I dni, the chemical potential of the ith component times the change in moles. And this only works at constant temperature and pressure. Otherwise, you'd have to have other terms. So what about for this? Here's a generalized gas phase reaction. Okay, like if we take stoichiometric coefficient A times compound A, gas, plus stoichiometric coefficient B, times with gas B goes to C, and D. All right. And this is at constant temperature and pressure. And these, like I said, these are all stoichiometric coefficients. This one as well. And so our DG is a little more complicated, you know, it's mu A dNA plus mu B dNB. So you just have to add these all together. Okay. And then you have to play the game with the dx, right? Dx. Remember that you have to take any reactant, change in moles of A as a reactant. You divide, sorry, that should be a capital A. You divide by the stoichiometric coefficient and you put a negative sign because it's a reactant, which is the same as minus dNB over B. Okay, so we're putting everything on equal footing by dividing by the stoichiometric coefficient, which I explained last time. For products, we just have to divide by the stoichiometric coefficient because products are forming. So, so the extent of reaction parameter is going from 0 to 1, so it's getting more positive. So are these things. So we don't have to bother with changing the sign there. Okay, so if you simply, okay, so now we have that A minus A dx is change in moles of A, minus B dx is the change in moles of B. And then we have C dx equals D moles of C, and little d dx, I love that one, is dNd. Okay, so so now I'm going to substitute these in, and we end up with dg equals mu A. So instead of dNA, I have minus A dx plus mu B minus B dx plus mu C dx, right? Plus mu D dx. And now the nice thing about this is I can take and I could factor out the dx. And actually I could divide by it and move it to the other side so I get what I want, dg dx. And now I just have to worry about these factors as minus A mu A. This is going to be minus B mu B plus C mu C plus D mu D. Okay, so it's very similar to what I had before, except I only had A and B, and one was positive and one was negative. And if I rearrange this, well, with the products first, okay, and then now if they're all gases, okay, then I could put in this expression that the chemical potential of a gas is the chemical potential of the pure gas at 1 bar plus RT times the log of the partial pressure of that gas. Okay. Then I have D, and the same thing again. UD0 plus RT log PD. And now I start with now I'm going to the reactants. So I'll be subtracting these. So what I've used here is that mu for gases, the chemical potential of the ith component is the chemical potential of the ith component in when it's pure form at 1 bar pressure plus RT times the log of that partial pressure. So now we're talking about a mixture. Cp of ith component of a gas mixture. And so this is what I've plugged in for every one of these, right? And so if we just go and group, this is all dg dx. And now you could see I have C mu C plus D mu C mu C0 plus D mu D0 minus A mu A0 minus B mu B0. Okay, that's a big term. Then I have to put the C with the RT log PC. But I can actually realize right away that this is RT log PC to the C. And the same is going to be true for the D term. And not quite for the A and B, right? Because I have a negative sign here. So minus RT log P A to the A minus RT log P B to the B. All right, so let's see what we got here, you know? So this first thing, each of these is the number of moles of each component multiplied by the, for a pure substance, right? This is for a pure form, right? So this is the standard molar Gibbs free energy of pure C, okay, which is the same as a chemical potential in pure form, 1 bar. It's really the same. This is the same as this. But anyway, so when you add up the number of moles of each component of the products times their standard molar Gibbs free energies, and then you subtract the same for the reactants. Well, what is that? You're adding up the Gibbs free energy of the products when they're in their pure form on that side and subtract the Gibbs free energy of the reactants. That is simply delta G0 for the reaction. So that's what this is. I could put reaction there or I could take it away. It means the same thing. So that certainly makes this a lot easier. dg dx equals delta G0. Now I have the rest of this, but I can clearly factor out an RT. And then I have log PC to the C plus log PD to the D minus log PA to the A minus log PB to the B. And that is RT log PC to the C, PD to the D over PA to the A, PB to the B. And that should look pretty darn familiar to you because this is what we teach you. It's the equilibrium constant. It's not in Gen Chem, but it's not really the equilibrium constant yet, right? This is Q. This is the reaction quotient. This is not constant yet. It can be anything. We can calculate this at any point in the reaction. It changes throughout the reaction. So it changes as the reaction goes on. Okay. So, you know, the shorthand version of writing this would be that dg dx equals delta G0 plus RT times the log of that reaction quotient. All right, so let's just go over what I kind of maybe didn't do such a good job on while I was looking at the curve. And I want to tell you about the sign, okay? So if dg dx is, okay, if it's positive, remember this is the slope of g versus x. if it's positive, then it means that at that point, the G versus X curve has a positive slope. Okay. And you know, it's not going to look, it's going to look something like this, right? It's going to look something like that. But at some point, if it has a positive slope, what does that mean? That means that in order to decrease G, the reaction is going to have to go in reverse. So to decrease G, which is what the second law tells us we have to do for it to be spontaneous, the reaction goes in reverse. This computer is like so hot. It's like I can hardly touch it. So to decrease G, reaction goes in reverse. Okay, if the slope is negative, okay, G versus X, to decrease G, the reaction has to go forward. It's like follow the down of the arrow, follow the direction that lets G decrease. And if dg dx equals 0, then the reaction is at equilibrium. And again, what happens under standard conditions? So here we have a much more complicated expression. But still, under standard conditions, all of these things equals 1. So this is still the log of 1, which is 0. So dg dx is totally determined by the sign of the delta G 0. So that tells you that, that the delta G 0, you know, if it's negative, the reaction will go in reverse. If it's positive, that's positive. If it's positive, the reaction goes in reverse. If it's negative, the reaction will go forward, right? That's why you have to add a little fine print to when it says, you know, in freshman chemistry, you say, oh, delta G 0 is negative, the reaction is going to go forward. And now we have to put under standard conditions because we know better than to just listen to the Gen Chem take on it. What's happening with this crazy? Oh, let me try it here. My display is a bit weird right now. Okay, there it is. All right, so I need to now tell you about what happens if solids or liquids are in a reaction. But you know, you already know what happens when solids and liquids are in a reaction because you've been writing equilibrium constants since freshman chemistry and you never include them. But this is why you never include them, okay? The reason is that we use for gases mu I is mu I0 plus RT log PI, which was derived a couple of days ago from the dg equals VdP, and we integrated this, ... and we got to something simple like this. But for solids and liquids, mu is equal to mu 0 period. That's it. This is negligible. Okay, so so it really just makes it simpler. So what I'm going to do is I'm just going to show you. I have a handout that I sent you, and it basically looks like this. So this is what we just did. I'm not, I'm just going to go through this. This is what I just wrote down for you. This is for the reaction, this reaction here with everyone being a gas, all gases, okay? So we started with this, like we always do, ... We ended up with dg dx equals, remember we had the A term, the B term, the C term, and the D term. And we grouped all these together, and that was delta G0 for the reaction. And then we had these other terms that we put together, and we ended up with the RT log of this whole pressure ratio, that QP. So what happens now if one of these, so if there are solids or liquids, so in this example, I say, well, what if A is a solid? Okay, so the difference between this and the example we just did is that, before, when A was a gas, we had mu A is mu A0 plus RT log PA. And now we just don't have that part. Now, if it's a solid or a liquid, it's just equal to mu A0. So what that does is it gets rid of this term. So we're just going to cross out that term. So there will be no partial pressure of A in this equilibrium constant, or in the Q, which becomes the equilibrium constant. So, I just eliminated the ART log PA. That's gone now. And so we still have the delta G0 from all of them. Notice A still contributes here. It's not like A is, has no role. It's standard molar Gibbs free energy is still relevant to the delta G0 for the entire reaction. So it's included in here. So there is a role for A to play, but it is no longer, there is no PA in this QP expression. Okay, so solids and liquids, that's it. That's already done. Okay, so you just have to leave it out, leave out the pressure term. Okay, so QP no longer has any pressure relating to A in it, but mu A0 is still part of the delta G0 through this term here that I've shown you already. Okay, does that make sense? Okay. So the QP now just doesn't have the PA in it, but everything about it is the same other than that. And when we set this equal to 0, again, we'll get delta G0 is minus RT log of now K, because this is 0 at equilibrium. And then the K also doesn't have a pressure for a solid or a liquid, and that's why they're not there. Another thing that comes to mind is when we derive this, the relationship mu A is mu A0 plus RT log of P. This was really P over P0, remember? And that's why we don't give units to equilibrium constants, because these are really ratios. Every one of these pressures, is being divided by the standard pressure raised to the same power, which we just don't include because you've already divided by that one bar. So so that's why we don't have units either. So that's a cool thing too. All right. So what about aqueous solutions? Because we really care about aqueous solutions. So for gases, you know, we had mu I. Oops, why am I opening PowerPoint? I don't know. For gases, we had this, which I've written a million times now. For solids and liquids, we had this. Okay, and as you might guess, for aqueous solutions, we have something similar. So what we had here was the chemical potential equaling a chemical potential at a standard state. And as you might imagine, an aqueous solution is not going to have the same standard state as a gas. The standard state for an aqueous solution is a 1 molar solution. Okay, so we're always comparing, well, it doesn't look like we are, but we really are comparing to the situation for a 1 molar solution. So for aqueous solutions, the chemical potential of the ith aqueous component in a mixture is equal to the chemical potential of a 1 molar solution of that component plus RT times the log of the molarity of the ith component divided by the molarity of a 1 molar solution, which is 1 molar. And so again, we're dividing by 1. So we get to leave this out as long as we remember to use molarity units for aqueous solutions. So we can leave this out. As long as we use molarity. Okay. So if we go and consider a more complicated example, like suppose A is a solid in our reaction and B is aqueous and C is a gas and D is another aqueous component. So we have this reaction here, and you develop the direction predictor equation. You always start with this. So dg is, and really the fact that it's solid and liquid doesn't enter into it yet. You're still just writing mu A dNA plus mu B dNB. this is the same as the beginning. You know, this is the same as we did before. Okay. And then even the bit with the stoichiometric coefficients is the same. You know, dx is dNA minus, put a negative, divide by the stoichiometric coefficient. So minus a dx is dNA, etc. So then this is mu A minus A dx plus mu B minus B dx plus mu C, C dx, because it's a product now. And then dividing through by the dx, we get our derivative. The change in the Gibbs function with respect to x is C mu C. So nothing is different yet. It's only when we come to substitute for these guys, right, that we have different formulas depending on whether they're solids or liquids or whatever. So C is a gas, D is aqueous, A is a solid, and B is aqueous. So we have to use the appropriate, so for a gas, it's mu C0 plus RT times the log of the partial pressure. Okay, for aqueous, it's mu D0 plus RT times the log of the molarity of D, okay? Minus A, now A is a solid, so it's just going to be mu A0, period. Minus B, now B is again aqueous, so it's mu B0 plus RT log. Oh gosh. All right, it's not sharing anymore, but it didn't crash. B mu B0 plus RT log concentration of B in molarity units. So again, we group everything together with the zeros. Which becomes the delta G0 for the reaction. And then we have the other term, which we have an RT log of PC to the C, okay, plus RT log D to the D, right? Because we're moving this over there to just make it easier on ourselves here, minus, oh, well, there's nothing for A. So we just have RT log P, concentration of B to the B. So this is delta G0 plus RT log PC to the C plus log, concentration of D to the D minus log concentration of B to the B. And this is our QP. Well, it's not P anymore. We just call it Q because they're not all pressures. So we take away the P. And you could see if you had no gases, then there's going to be no pressure here. Okay. And also there are some minor things that I should probably point out, and that is that usually we don't put pressures with molarities. We would put them all in molarities, but that would just change the equilibrium constant by a constant amount. And, you know, I don't have time to get into all these different situations, but anyway, this works perfectly fine. So that's really the more general case of the direction prediction equation. And you could develop one of these for any reaction. I think I've covered all the bases with liquids, solids, gases, and aqueous. So how do you use it? So you have this wonderful equation. Which I'm just going to abbreviate that way. And so, of course, you know, you could calculate this delta G0. We could calculate it in a couple of different ways. You could be given the delta GF zeros of the reactants and products. So that's one very good way to get the delta G. You could be given the delta H0 and the delta S0, or delta HF zeros and S zeros, right, to calculate those deltas. So you would use these to get the delta H and the delta S. And then you'd use delta G is delta H minus T delta S to get the delta G0. Okay. You would have to be given the concentrations or the pressures of all the players in the reaction, reactants and products. I'm going to do an example with you shortly, so you'll see what I mean. Except the damn thing crashed again. So, given concentrations for aqueous components at any point in a reaction, and any pressures in bar for gases, you would substitute them into the Q expression and calculate RT times the log of Q. So you will have delta G0, you'll have RT times the log of Q. You would add these up and you will get dG dx. Now, by the way, the book in chapter 9, I have a couple of little sections to read in chapter 9, which are outlined in assignment 6, which is posted. On top of assignment 6, it says what to read, if you want to do that. When you get your dG dx, that's what it is. It's the derivative of G versus extent of reaction. But the book calls it something completely different. The book has a new name, and it calls it the reaction Gibbs function, which a lot of people use, but delta RG. So they write delta G0 for a reaction as delta RG0. That's what this is, right? Delta G0. Delta RG, it's like a delta G without the zero, but it's not really a delta. It's really a derivative. So, you know, why not just call it what it is? But the book calls it the reaction Gibbs function, and it has this symbol, just so as you know, okay? I hate the name. I think it's awful. I don't even know. When I first looked at, most PChem books do this. When I first looked at it, I started teaching PChem. I was like, what are they talking about? This doesn't make any sense. But I want to point something else out to you, and that is about the drawings. And I started to say this last time. So if delta G0 is negative, then you're going to have, obviously, this dot is going to be higher than this dot, okay? Because the delta G0 is negative, goes down. So then when you draw the diagram, make sure that your equilibrium is going to be on the product side. Do not draw me a diagram that looks like this, with the equilibrium on the reactant side. If the products are lower, the equilibrium is going to be on the product side. So this is just wrong, right? If the delta G0 is positive, then it's the opposite situation. Equilibrium is going to be on the reactant side. Now, how far over it is on one side or another, that depends on, how negative and how positive it is. And I'm not going to get real sticklerish about that, because this is actually more complicated, what's going on with extent of reaction, than I have alluded to, and I don't want to get into that. But if you know that you have a reaction like this with a positive delta G, right? This is the positive delta G here. And in most cases, like for most concentrations, the reaction is going to be going backwards, right? That's consistent with what you know from freshman chem. But there's also this region here where the reaction is going to go forward, and it's a smaller region. But if you have all reactants or mostly reactants, that reaction is going to go forward. So, so anyway, just to be aware of that you're going to have a smaller region where the reaction is going forward if delta G is positive. And you would never draw the curve like this. If you have this situation, you are not going to have the minimum over here. That's just wrong. So don't draw that. Well, if I ask you to draw this picture, a sketch of G versus X, and supposing it's exothermic, and you draw a picture like this, a lot of times I ask you to label the relevant features. So that means you have to tell me where the equilibrium is. You have to tell me what this is and what this is. And this is really just a sum of mu0 reactants. And I'm not asking you to write A mu A0 plus B mu B0 or anything like that, but you should give me something like this. If I ask you where is standard conditions, okay, so now here we have a delta G0 that's negative. So under standard conditions, which way is this reaction going? Delta G0 is negative. Under standard conditions, the delta G0 determines dG dx. dG dx will be negative because all those p's are equal to 1. Remember, that's a log of 1 is 0. So the Q term doesn't exist. No Q term. It equals 0. So if delta G0 is negative, under standard conditions, that reaction is going to go forward. So standard conditions is somewhere over here. I don't care where it is. It's where the reaction is going forward. I don't need for you to, because if we have reactions with interesting stoichiometry, it's very hard to figure out where it would be on there. So I don't expect you to figure that out. I might give you a set of conditions and say, where is this set of conditions on the graph? If it's very high in products, it would be over here. And you could say over here, it's on this side of this, it's over here somewhere. That's good enough, okay? All right, so I'm just gonna whiz through one problem because I want you to have one problem under your belt before we reconvene next time. And I really only have one more thing to do this semester, and that's go over how you get that Gibbs-Helmholtz equation, the log of K2 over K1. That's next time. And that won't take the whole time. So we'll do some more problems, but I want to show you this one problem. Oh, that's the wrong problem. Do I have it here? Oh, here it is. Look at that. It's right there. All right. Oh, I didn't put the reaction, but it's this bunch of biochemistry, FDP. This is, oh, I didn't put that down. Oh, here it is. Here it is. Okay, never mind. I want to write it all down. This is a step in glycolysis where fructose 1,6-diphosphate is converted to glyceraldehyde 3-phosphate. I can barely pronounce these things, and dihydroxyacetone phosphate. Okay, so we've got an FDP as a reactant, a GAP, and a DHAP as products. And it's giving you the equilibrium constant. Now look at this equilibrium constant. It's really very small. Okay. But the first thing it wants is for you to develop the direction predictor equation. And by this, I mean to start out with DG is equal to, and I'm just going to abbreviate these as F, G, and D, okay? So it's mu F, D, N, F plus mu G, D, N, G plus mu D, D, N, D, okay? And these are all easy, right? There's no crazy stoichiometry. dx is minus dnf, which is the same as dng and dnd. So there's no fancy stoichiometry stuff going on. So this is mu f. This is minus dx plus mu g dx plus mu d dx. The dx goes to the other side. And this is mu f plus mu g. Oh, sorry, minus mu f. So let me write the mu g first. Okay, now all of these are aqueous solutions. So this is going to be mu g0 plus RT log of G. Okay. Plus mu D0 plus RT log of D minus mu F0 concentration of F. Okay, so that's dG dx. And once again, we get to group mu G0 plus mu D0 minus mu F0. This is delta G0 plus RT times the log. And we have no powers here. G, D over F, okay? And this is our Q. Okay. That's the direction prediction equation. Okay, now it tells you the equilibrium constant, 8.9 times 10 to the negative fifth is the K. All right, so then it asks you, what is the standard Gibbs free energy change? Well, this is where we get to use our newly derived formula. This is minus RT times the log of K. Okay, so just put that number in. So this comes out to minus 9.33. So this is negative. So the delta G0 is positive. It's 23.1. So I put in R is 8.314 times 10 to the negative 3 kilojoules per mole Kelvin, 298 Kelvin. Okay. Yeah. That's what I plugged in for these two. And this is your delta G0. Wait. Okay, yeah, 23.1. Okay, so now, next part of the problem, it says, a typical concentration of reactants and products in biological cells has, and you notice that these are very, very low concentrations. So the products in this reaction at this point have extremely low concentrations. The reactant has a much higher. And low product concentrations. Cells are really good at controlling the direction of a reaction by controlling the concentration of all those chemical species in that reaction, so that it can drive a reaction forward, even if a delta G is negative, or backward, even if it's the wrong sign. So we're going to calculate the dG dx. So it's delta G0 that we already got, plus RT times the log of that ratio, which is G D over F. And so that this is going to be 8.314 times 10 to the negative 3, 298 times the log of, okay, G is 1 times 10 to the negative 5th. D is the same. And FDP is 1 times 10 to the negative 2. So this is actually 10 to the negative 8th, the log of 10 to the minus 8th. So, so that this whole term is equal to negative 18.4. So now let me not put that because it's a little confusing. So we have 23.1 for the delta G0 plus this term is negative because the log of this is going to be negative, and it's a big term, 45.63. When you add that together, you see that the dG dx is actually negative. So the slope is negative. So which way, even though the delta G0 is positive, this reaction is going to go forward, okay? Because of the small concentration of reactants and the high concentration of products. And already gave out again. All right. So the slope is negative, right? This is a negative slope, okay? That means that the reaction is going to go forward. And this is despite the positive delta G0 for the reaction. Okay, so that's why you have to say if delta G0 is positive, the reaction goes in reverse under standard conditions. These are not standard conditions. And how would you draw this? It asks for a sketch. All right, well, we have a positive delta G0, so we know we're going uphill here. We know that the equilibrium is going to be on the reactant side. Where would standard conditions be? Standard conditions, where would they be? Somewhere over here, right? Yeah, but the right and left is also confused on this
On the
thing.
right.
Yeah, so the standard conditions would have to be somewhere over here because the slope is positive, and we know that under standard conditions it would go that way. And this is the conditions of what part of the problem was that? Part C. Yeah, somewhere over here. All right, I'm done. How's everything going?